Okay, today's guest is the Mr. Geoff Huston, the chief scientist of the APNIC. Thank you very much, Geoff, for your time this time.
A pleasure.
So I'm always amazed with your presentation to put the very good outlook for the internet and how we have come to here and then where we are going. Well, how do you tell the story about that?
Well, in some ways, the way the internet is being driven can be traced all the way back into the early days of the telephone networks. Yeah. And to my mind, I think the story is logical but not well understood. The explosion of the telephones on the world at the time was amazing. Yeah. All of a sudden, instead of sending a telegram or even worse, sending a letter, you could talk to that person as if they were in the same room. Mm. It was an extraordinary tool, and it was used for people, but also used in the corporate world because it was all about the projection of power.
Okay.
You could only have really big companies if you had a really accessible communications network based on the telephone. You can't run a multinational on telegrams, it never could work. And when we kind of looked at that evolution of the telephone, it was an odd evolution. It may not have seemed at the time, but it was expensive. It's expensive to hang wires on poles.
Okay, yeah.
It's expensive to drag a huge numbers of wires through suburbia to every business or residence, everything. Mm-hmm. And all of those wires, you might recall in the 1890s and 1900s, there were pictures, certainly out of America, of these streets which had these poles with 100, 200, 300 cables hanging off them.
Right.
This was crazy.
Yeah.
And it wasn't long before they realized we can make it cheaper.
Yeah.
And we can make it cheaper by putting multiple conversations into the one conductor.
Okay.
And how do you do that? With electronics. And the first stuff was valve-based, of course, and it was frequency division and it was frequency multiplexing.
Yeah.
So you map conversations into higher frequencies, you push them all down the one wire, at the other end you pull them apart, and so on. It's a bit like the radio spectrum today, old stuff.
Right.
Still expensive, but not as expensive. And of course, the cheaper you make it, the more accessible it becomes, the more people use it. Mm. And the telephone network through the 20th century sort of got better at this. Not only did it change the way that it shared the wire, but it then also changed the way it did switching.
Okay.
And instead of lots of people at desks connecting cables into sockets and so on, we used automatic exchanges, all a case of driving it cheaper. Mm-hmm. But there was fundamentally something that happened around that time, around cost and scarcity, which was this emergence of the computer.
Okay.
And the computer itself is extremely old. The transistor is not.
Right.
Transistor is 1947, and the integrated circuit about 10 years later, about 1958. Mm-hmm. So much smaller than a valve. Right. So much less power, so much less heat.
Yeah.
Everything was kind of revolutionary. And once you started to use electronic devices, silicon, inside the telecommunication system, you could make a much cheaper telephone network.
Yes.
It still had the same architecture. Mm. At the end were dumb devices, speakers and microphones, telephones.
Yeah.
In the middle was all the smarts.
Mm.
And that model persisted for around about 30 to 40 years. Mm. At the same time, though, the computers were getting better and more people were using it themselves.
Yeah.
Big mainframes. And even in the mid-1980s, the first of the so-called personal computers.
Yes.
The IBM PC was the, thing that shocked the world, but it wasn't the first. But all of a sudden, companies didn't have one computer, had thousands. They had a whole heap. And how do you let them talk to each other? Because they weren't electric typewriters. That wasn't their real, it was allowing the data to be shared, allowing these devices to be windows on a much larger piece of data.
Yeah, that's actually a very big change. So that you said that in when the telephone emerged in this world, the telephone terminal was a really, really simple speaker and microphone cascaded with the two wires. Yes. Then the intelligence is all on the network side. Then we have the computer, and the computer is getting smaller and smaller, and then affordable, more and more affordable to the even the person. So that's a huge change of that.
But there was another change.
Right.
As humans, we're not very good at reassembling data. For what I say to be understandable to you and to everyone else, we have to preserve time and synchronicity. You can take the words I say and garble them, you won't understand.
Right.
But with computers, I can.
Yeah.
I can say, this is packet number 1. This is packet number 3. Oh, sorry, I forgot to send you packet number 2. Here's number 2. And the computer at the other end goes, sure,
yeah,
I can reassemble this.
Right.
That was one of the biggest thought bubbles, I think, in the history of networking. Because all of a sudden, you didn't need to switch the hardest thing of all. Telephone networks switch time.
Yeah.
That's really hard, really expensive. Time division switches cost so much money that most countries could afford 2. In Japan, I'm sure there might have been 3, but there weren't 1 million.
Right.
There were 2, because they cost a huge amount, because switching time is really hard.
Yeah.
But if I can make the intelligence go out to the edge and make a computer and say, look, scramble the middle, juggle time, do what you want. I'll reassemble based on, if you will, some header information. This is packet number 4 of 20. When you reassemble the data, put it in that slot there. Yeah. Then all of a sudden, I can actually run cheaper networks. And this was the thought behind packet switching. That instead of stream switching, you just put it into packets with the computers at either end, and you take all that state out of the network that preserves time, and now you're just switching packets. 1966, really. Invented in a number of countries, the French with Cyclades, Louis Pouzon, the British Physics Laboratory. I might hash it up. I think it's Di Davies, but there are a few of them there. And interestingly, in America, Bob Kahn and Ben Cerf and others were working in this area of switching packets.
Yeah. That's around 70.
It's a 66, 67, 68, around that space.
Right.
And there was this glimmering that this could make networking cheaper. And not just a little bit cheaper, really cheap.
Really cheap, yeah.
But at the time when they looked around, who needs networks? And the conventional answer is telephone companies need networks.
Yeah.
And the telephone companies were kind of going at the time, love your work. It looks amazing, but we already have a telephone network. So for us to use your technology, we're going to have to think about it. It's going to take a little while. 10 years, 20 years. We move slowly. Our investment cycles are very long and ponderous. These are big networks. And while the promise was there, the need for urgency wasn't. But the invention of that integrated circuit back in 1957 was amazing. Because very quickly we found we could increase the quality of the optics to etch the circuit on the silicon chip.
Yeah.
We could move from visible light to X-rays and get even finer granulation. Instead of having tracks on silicon that were the width of a finger, we can't do that. You could make little tiny features the size of a human hair. All of a sudden you have 1,000 transistors on a chip. 1 million. This stuff was getting better every year. And Gordon Moore, the CEO, one of the co-CEOs of Intel in the mid-60s, observed that we can double the number of features, the number of gates on a silicon chip every year. So every year these computers are twice as fast. but at the same price.
Moore's law, so to say, right?
It's Moore's law.
Yeah.
But think about what Moore's law means. I bought this really good computer 2 years ago. But the one I bought yesterday is twice as fast and cheaper.
Exactly.
And so the computer industry was never going to wait for 20 years.
Okay.
That's a factor of 1 million if you're doubling every year. 1 million times cheaper, 1 million times more. They can't wait.
Right.
And so when the telephone company said, come back later, the answer from the computing industry was, you're not interested. We can see that. We're going to forge a different path. And I suppose the divorce wasn't conscious, but it happened. And the first thing that really fired up was Ethernet, local area networking.
Right.
Ethernet was revolutionary because there was no network.
No network.
It was a piece of cable.
Oh, yeah.
There was just computers attached to a cable. There was no master controller. There was no timing signal.
Yeah.
All the packets were self-clocked.
Right.
Hang on a second. You mean to say that piece of cable is a network? Yes. So who runs it? All the computers that attach to it.
Yeah.
How do they sort themselves out? Well, they all run the same Ethernet access protocol.
Before Ethernet emerged to this world, we need to connect point to point, every computer.
Points to points, and we kind of put switching functionality inside computers.
Inside computer.
But all of a sudden in Ethernet, you kind of realize, what do I want out of a switch? And if all the ends are doing the job,
Right.
what I want out of a switch is nothing.
Nothing.
So again, that was one of these revolutionary thought bubbles like packet switching that kind of went, I don't need big fancy networks. I need small networks that do as little as possible.
Right.
So at that point, there was sort of two efforts to try and make packet switching bigger, more scalable. One was based largely on the French direction, which emerged into X25 packet switching from the telephone company.
Yeah.
Big switches, big functionality. You kind of treated computers as far dumber than they really were. Far dumber. They put in a stream of bits, you framed it up into the network, and the same stream came out the other end.
Right.
The network did all the work. The IP model took the Ethernet thinking and translated it. And it said, I'm going to shove it into packets. And I'm just going to send them into the network. They might get reordered. Yes, they might. Some of them might get lost. Some of them might get duplicated.
Yeah.
How are we going to make it better? Let's not bother about making the network do that job.
Yeah.
Let's make the computer at the other end
Right.
reassemble those packets and put them all in neat order.
Again.
Yeah. And it recreates the data. You've lost nothing.
Right. So the internet is actually basically emulating the Ethernet itself.
Yes, there is nothing in the network.
Through the packet.
Just throw the packets in and the other end reassembles it.
Right.
So much cheaper. So much faster.
Right.
When Ethernet came out, it was 10 megabits a second. We were running kilobits. You kind of go, wow,
Yes.
so fast.
Yes.
When we translated that into IP, we got the same phenomenally fast and cheap answers. So the Americans, when they started building in the late 1980s, supercomputers, the country, I think, could afford 6 at the time. They were really big. And they said, well, we want this to be a national program across all the universities, and not every university is going to have one. Somehow we need to get researchers to computers. So part of the federal program was we need a network, a high-speed network, across the entire American academic and research network that connects to these computers. They took the early internet model, which has been funded as a quiet little model with a few contractors to the Advanced Research Project, and said, can you do it? And the answer was, well, we think we can. We think we can. And in 1988, they announced the National Science Foundation Network. 1.5 megabits per second backbone. You kind of go, that's bigger than a telephone company. At the time, that was such a big announcement.
Yeah.
And every other country was sitting there going, we want one. But more to the point, we want to connect to yours. And I found it amazing from the Americans. They kind of go, yeah, join us. Join us. And it was quite open. The technology process, which became the IETF, anyone could come.
Yeah.
And instead of charging for RFCs, they were there online. They discovered all this terminology about making it open, making it cheap. The telephone companies have been working on the Open Systems Interconnect profile. And it was a worldwide effort, and it was getting nowhere. I think the UK were one of the few that actually had an implementation called the Coloured Book Protocols.
Right.
But by the time IP was just washing over the sector like a tidal wave, it's just like, right, it's all over. We're running IP. And IP was almost an accidental victory. And it was a victory because it kind of worked with Moore's law. It worked with increasingly capable computers. It kind of worked by pushing cost to the edge, keeping the network as cheap as possible.
Okay.
And all of a sudden, non-professionals like me, working inside the academic sector, not the engineering areas of comms, were able to build national networks on our computing knowledge, not on our communications engineering knowledge.
Right.
We just bought the excess of oversupply for the telephone companies, the bits of wires that we're going to use in 5 years' time, and said, right, that's it. We'll buy it from you right now and run IP over it.
And that's your, the story to you get involved in AARNet.
Well, that's how I got involved in AARNet. It was straight from the computing side.
Yeah.
But it was all about this excitement. There's nothing better than working in an industry that has to reinvent itself every 2 years. Constant surprise, bigger, faster, cheaper.
Right.
All of a sudden, the desktops became, smaller laptops became portable, or the iPhone came out. This astonishing amount of computing started to work in our pockets.
Yeah.
Who would not want to work in an industry like that, where, every year it's something shocking and surprising?
Right.
So I actually put this all back to, we've pushed the model of integrated circuits. We're now up to 1 trillion gates. 1 trillion on a single chip, with a reliability factor that's staggering. I would have thought as it comes out of the factory, here's 1 trillion gates, and they turn the power on, and it goes, I'm alive. You'd sit there and go, oh, thank you, that's brilliant. But they regard this as a matter of course. Of course it works. We're good at our job. And they are. So the internet kind of followed behind that, filling in the pieces. And we use that capability everywhere.
Okay.
Fiber optic systems. How do you get 1 terabit per second out of a cable? Really good signal processing technology. The better that chip, the more signal you can salvage from the damage caused by the glass. And the only way we can get these current, 28 terabit cable systems that we're laying today is because of phenomenal digital signal processing. And so the industry continues to reinvent itself time and time again.
Right.
It's a fascinating place to work in.
Right. Well, you said that the computing power is, doubling every year, but
These days it's every 2 years.
It's every 2
We're
years.
slowed down. That's not slowed down.
But at the same time, that there's a limit of the light speed.
You might think so,
Right.
but we've changed something quite fundamental in all of this.
Okay.
Computing is abundant, not scarce. Storage is cheap, not expensive, and abundant.
Right.
Communications is abundant.
Right.
Terabit cables are huge. We have a few hundred of these around the world, and we're going to do a few thousand because the cost of the cable hasn't changed, but the capacity has gone 1,000-fold.
So light speed is not changed, but the multiplexing factor is
Right. So if I want to distribute a service, so it was Microsoft selling out copies of Windows 95 or whatever. I used to put it on a couple of servers in Seattle and say to the world, come and get it. And the rest of the world had to use a network, a scarce network. And there was a black hole in Seattle when everyone converged. And poor old Microsoft was building new servers, new capacity to distribute their software. We don't do that anymore because we're in abundance. We don't provision in a model that says it's over there, use the network. It's cheaper and faster to push a copy to everybody. And the classic example of the video streamers, the YouTubes and Netflixes of this world, when you run a video, they're not serving it from somewhere far away.
That's right.
A copy of every video is in a local data center a few kilometers away from most people, no matter where you are. We can do that because it's abundant and it's cheap. And we've changed the provisioning model to what I call just in case.
Okay.
I don't know if you're going to watch this video, but just in case you do, I've already loaded it here. You're welcome.
Everything is here.
Everything is here.
Very close to you.
If you're still using electronic mail, I know I am, it follows me.
Because it is cheap.
It's cheaper to preload it where I am than it is to make me haul my packets around the world. So interestingly, the network is becoming shorter again. And the content distribution networks are picking up the long-haul load, not as public infrastructure, but actually as private. The big hyperscalers are now laying their own cable systems, fully owned. And it's a different model of communication.
It is quite different because you said, as you said, that the internet is like emulating the Ethernet.
Well, emulating the telephone network. And all of a sudden, we're now building a different model. And that different model is we're going to do a just-in-case delivery system where we, just in case you might want it, we've got so much capacity. It's cheaper to pre-provision everything close to a user. Now, the other part of this is, in communications, it's distance that costs.
That's a communication.
And in fact, I think it's distance squared. Distance is terrible. So speed of light. It only gets a problem when you've got distance. The shorter I can build a network, it's faster, it's cheaper, it's easier. So let's build a new network that says it's only the last mile. The link from the local hub to your workplace, your home, whatever. And these networks are about 5 kilometers long on average. That's an easy problem to solve.
Because that's cheaper.
It's cheaper. It's only 5, and I can make it so fast.
When the Ethernet emerged, the Ethernet was cheaper.
At time, yes. And it was quick. So now we're building these millimeter wave mobile systems, moving from 5 gig up to 10 gig to 16 gig. And the answer, gee, that's difficult. The answer is, well, if you're only doing it over a couple of kilometers, it's not. It's actually quite easy over short distance. But how do I get stuff? And the answer is, we'll push it at you. Everything you need is going to come around you. So it's a different model of the service that we use the network for. And the network kind of shrinks into that last mile of going, well, this is the only bit that's shared infrastructure now. The rest is just part of the service and content infrastructure that other people are building, and that's fine. And it's cheap because the whole Silicon Revolution has made this really, really, really cheap.
Interesting.
And so those kinds of things are shaping the future. So is routing important?
Routing?
Not really. Because over the last mile, there is none. And all those long-haul networks are private. So why do I need to understand the world's topology when no packets fly over it? So some parts of the internet we thought were important now probably aren't. The world will have a lot more pieces of silicon. From billions to trillions is pretty easy. It's just sand. We can make a lot of it. We're very good at it. Do I need to uniquely number every one of them? And the answer is, well, no. Not globally. As long as they're uniquely numbered amongst their immediate neighbours, that's okay. So you can be one in Japan, I'll be number one in Australia. Every country will have overlapping numbers. Doesn't matter. So how do you define a network when the addresses actually don't matter? Names. And the other thing that's revolutionized the internet over the last, I'd say about 15 years, and people go, what's happened to V6? And the answer is, it's less important. Our whole security system, our service infrastructure, and our content delivery networks are name-based. I go to the name, not the address of that name. Its location doesn't matter because it's everywhere. Abundance. This is a new way of thinking about networking, where you think about it as content and service being delivered close to you, and the distinguishing factor, that content, not the others. And I want to know that it's authentic, is based around the name that we use. So who would have thought, I certainly didn't in the early days, that the DNS was way, way more important than IPv4 or v6.
Then how about, how do you think that the numbers will be? We are now at the APNIC conference. APNIC is dealing with the numbers.
Well, my job in APNIC is to keep an eye on many things, including the future.
Okay.
And the models that we used in the early 1980s around packet switch networking were based around this paradigm of telephony. The telephone number mattered, the address mattered. And as we built a global network, we said, we need global uniqueness of addresses. And that was a fine conclusion. But as we keep on changing the network, trying to make it bigger and cheaper, and bigger is a really big, thing, you kind of got to wonder, what is the role of addresses in an internet with 1 trillion devices?
Right.
Or 10 trillion, uncountably large. And the answer really is, I don't think addresses matter globally. They matter on your local network to stop packets getting confused.
Okay.
So there are many Geoffs in this world, but in my house there's only one, and that's a good thing.
Okay.
And I think it's a similar analogy. That you need unique addressing when collisions are a problem. But when it doesn't matter, it doesn't matter. And there are millions of Geoffs, I guess, all the other Geoffs, but it's okay. Because unless we all sit in the same room and say, hey, Geoff, it really is okay. And in our case, addresses are playing that role now of being a distinguisher in a vanishingly, not vanishing, but in a smaller and smaller realm. It's names that are globally unique. And it's names that are the underpinning of security. They're the underpinning of our service environment. They matter.
Okay. What do you outlook for the future in this world, in the internet?
Well, there's various folk that have been saying the end of Moore's law. I've been guilty as well.
Oh, really?
Because when you get down to a feature size of 1 nanometer on the chip, that's about 10 atoms wide. At that kind of size, and that's pretty small,
right?
The electrons stop behaving nicely and tunnel through the barriers.
Right.
And I'm not sure that we can make that work for much longer. But the chip guys aren't giving up. They're creating 3D lattices of silicon. Lattices, frameworks, pages, where instead of making it smaller and smaller in a flat plane, you start to build silicon castles of processing. If we can get that right, there's a whole new breadth of life for Moore's law, and the continuing evolution of silicon just gets better. If we can't do it, the party stops. If we can't do this kind of multi-layered lattice work in the underlying chip, then it ceases to get bigger, faster, better. Whoever's sort of in a dominant position stays there, and the technology train sort of comes to not quite a halt, but it certainly slows down a lot. So I'm looking at that work on basically how do you make chips even faster with great interest. I am not the physicist in the definitely not. I only did it for a year or two. But I think that's one of the key areas of what will sustain that growth. If we can sustain that growth, then what we're going to find again is we can keep pushing at this model pretty hard. And there's no reason to suspect we can't at this point. There's no insurmountable barrier looking at us in the face.
All right, then we do hope that someone achieved that kind of the evolution.
They're working at it right now, and more power to them.
Right.
If I was doing a PhD around this area of microstructures in silicon, it'd be on 3D lattice work.
Yeah.
Yes.
Oh, wow. Thank you very much, Geoff. Very, very good.
Been a pleasure.
Thank you. Very good insight, and your wisdom is really welcomed by all our committee members. Thank you very much.
Thank you.
Thank you.